Hi everybody, Dr. White here, continuing our work on setting up integrals that compute volumes. Wanted to do one more example. It actually is exercise 7 in our textbook, and it's associated with figure 19b. So let's go ahead and pull up the textbook and get a look at it. So let me see, there we go, textbook. And right above the exercise 7 in section 6.2, we see two figures, and I'm concerned with the one on the right where I'm waving my mouse, figure B there. So what we've got here is, this point right here is the origin in three-dimensional space. Now there is an x-axis running this way. Those are the positive values for an x-axis. There's a y-axis running this way. Those are the positive values on the y-axis. And there's a z-axis running straight up and down. And that's the positive z-axis. And those three axes are perpendicular to each other, and they make the way that you locate things in three dimensions. Now, associated with those three axes would be three important planes. If you look at just the x-axis and the y-axis, then they they cover a plane that you can think of as flat and at the bottom, and that's called the xy plane. And then there's two other planes that are important that stand straight up perpendicular to it. One of them contains the positive x-axis and the positive z-axis, and that's the xz plane, kind of to the back left. And then there's another one consisting of the positive y-axis and the positive z-axis, and that's the yz plane, kind of standing there on the back right. And that corner you're looking at, that's the origin. Now, the figure we're interested in is bounded below by the xy plane, and also bounded to the back on both sides by the xz plane and the yz plane. And then it is also bounded by another plane, the plane that contains the point A on the x-axis, the point B on the y-axis, and the point C on the z-axis. And so they have drawn blue straight lines between those points, and there's like a triangle there. That triangle bounds the region from above, as it were. And so the figure we're looking at is a solid that has four sides. All four sides are triangles, and we want to find the volume of that triangular prism-like solid. So how shall we do it? The suggestion given here in the figure is to do cross sections, and those cross sections are, let's see here, they are going to be parallel to this YZ plane in the back. And so that means that they are going to be associated with different x values along the x-axis. From x is 0, and that would give you a right triangle that's on the YZ plane, all the way up to x is equal to a, where the triangle shrinks down to nothing. And all of those little cross sections are right triangles. They have a base that's in the xy plane, and then they've got this vertical height that's over in the xz plane. And so if we can find a formula for the area of each of these cross sections, multiply by the little dx thickness, and then sum up with an integral, we'll get the volume for the entire figure. That's the idea that we have in mind. Let's see if we can carry it out. Okay, so here I've got a picture of one of these arbitrary cross sections with the base in the xz plane, with its base in the xy plane, and its height in the xz plane. Let's first think about the base. So this line here, if I look down at it from above in 3 space, then it would look like this. So here's the origin at the x value 0, and here is that x is a point, and here is the arbitrary x point that determines where the base is, and here's the base. And so the base itself is going to be the length of the vertical length of that segment. Now, thinking back to the picture, if I can pick it up for a moment, yep. The lower end of the segment is clearly at the value y is 0, and the upper end of the segment is at some y that lies along this line here. Okay, so I have drawn that line, the one that goes from the B on the y-axis to the A on the x-axis. I've drawn that line in the base of the solid on this two-dimensional representation of the base. And we can see that the height is simply going to be the y-coordinate for that line. So we just need to find the equation for that line. And there's, of course, a couple of ways you can do it. We've got 2 points we know are on the line. One is x is 0, y is b, and the other is x is a, y is 0. You could use point-slope formula, or you could use slope-intercept formula. But one way or another, you'll end up getting that y is b minus b over a times x. Okay, and so that y minus the 0 height would be the base for our triangle. Okay, so we've got a formula for the base in terms of x. It's b minus b over a times x. Now we need to also think about the height. Okay, so heading back to our figure, that's this line here where I'm waving my mouse. Now that goes from a z is 0 level to a z is some level that's given by this blue line here in the xz plane. And so I want to make just a two-dimensional projection to show you that. So back over in the notes, what I've done is made this two-dimensional projection. Here we have our x-axis. Now, this is really the z-axis, folks, but we're not used yet to thinking of like, we're used to thinking of like y as a function of x, and not so used to thinking of z as a function of x. So I'm just going to call it the y-axis for now, but really this represents that positive z-axis. And so we're looking at the back of the figure from behind here. And so we're seeing the height of that triangle. The triangle itself is headed straight into the page from that height, okay? And so we just need to find that height, and that height will be a line containing the points 0, c, and the points a, 0. And you can find that equation however you like, and it turns out to be y is c minus c over a times x. So the height, so that's actually what's along the z-axis, that height is c minus c over a times x. So now we got a better picture of our cross-section because we can label the base and the height on it. It's a right triangle, so its area is 1/2 the base times the height. And so when you multiply those things together, you can factor out clearly a b from here, and you can factor out a c from here, and you get 1/2 bc times 1 minus 1 over ax squared, okay? So the thickness of the figure is dx, because we make a little change along the x-axis to get a thin little cross-section. And so the little volume would be that. Add up from x is 0 to x is a, we'll get the volume of the entire figure. So now we just got a little integral to do. How shall I do it? I'm actually going to factor out the 1/2 bc. And I'm going to write this fraction as a over a minus x over a to have a common denominator of a. So I've got a minus x over a that I got to square. I can now factor out an a squared away from everything. And so I've got that outside now. And now looking at this integral, do it how you like. I'm just doing a little guess and check and thinking, oh, it's got to be, something cubed over 3. And when I check, I see I need a minus as well. And so I get an antiderivative of minus a minus x cubed over 3. evaluate between 0 and a, and after a small bit of work, you get this. Some of the a's cancel, and you get ABC over 6. Okay, so nice little convenient formula there, similar to the formula for a right triangle in 2 dimensions in some sense. Okay. Well, let's see. I think that's all I wanted to do for this section. So have at it with your, with your practice homework problems, and we'll be talking about this material in class soon. Bye-bye. Well, bye-bye soon. Let me find Chrome here. Come on, Chrome. Aha.